Okay, so the question is, how do we know what value of k to use, right? So remember in a previous lecture, I'm talking about the within SSS, right? So within SS. So basically, we need to extend this concept, right, of within SS. So we know that within SS is degree of incoherence of the cluster, right? Incoherence, not the coherence, okay? To compute the inconsistent value of the set of clusters, right? So basically, we can compute, right? Calculate the sum of the incoherence values of all the clusters to create it. So that's the value of the total of within SS. And then we can plot this total of within SS for each value of the K. Okay? So what that means is, so in this example, right? So idea is, so let's say we have two clusters, right? I mean, in this case, when the K is equal to 2, right? Because we have two clusters. And then in this case, we can compute the total within SS. So we can have a within SS for the cluster 1. And then within, we can compute the WSS for each cluster. And then we can add these two, right? And then we can get the total, WSS, right? So when the K is 2. And also when we have K is equal to 3, right? So let's say when the K is equal to 3, that means we have 3 clusters, 1, 2, 3. And then we can compute the WSS for the cluster 1, WSS for the cluster 2, and WSS for the cluster 3. And then we can compute the total WSS, right? And then something like this, okay? So we can plot this. We can plot this idea. Okay, I'll show you. Let's see. Let's just delete this, and then where is the plotting? Oh, so once again, please do not pay attention to the actual implementation. Okay, so this can be done in Python, R, and right? So like other languages. So do not worry about implementation. I want you to just focus on the concept. Okay. So the concept here is, let's just run, and then fit, and it's not this one. Yeah, I think this is the one. Okay, hold on. Okay, so yeah, so this is the one. So don't worry about the implementation at this point. Just let's take a look at this plot. Okay, so you know that this is total within SS, right? Across the clusters. So this total within SS, and then this is a K value. So when this is a K is a 2, you know that WSS is really low, right? So when there's no cluster, your SS total within SS is 22, right? About 22. But when you have two clusters, this is dramatically reduced all the way down to 2 point something, right? It's really small value. And then when the K is equal to 3, this is not as significant. I mean, you know that this is dramatic drop, right? And then there's some drop, but after 3, there is no really no reductions in total within SS, right? So there's no reduction in degree of inconsistency. Okay, so by the way, this looks like elbow, right? Elbow. So the best for the best K value is probably either 2 or 3. Okay, you usually choose the best K value when there is a dramatic drop, right? So either 2 or 3. But after 3, the reduction is not really significant, right? So the best the K value is either 2 or 3, right? By the way, this is look like elbow, and then you choose the value in this area, right? Okay, usually. Okay, now having said that, now let's take a look at the this k value, right? Okay. So we plot this the value, then we can choose in this case we can choose our k value to be either 2 or 3, right? So the lower value of k means that larger clusters, meaning the less number of clusters, right? Oops. And basically it means that lumping more data points into the cluster. So that means increased incoherence or the increased reading access. Okay. So if you choose really too small k, this could be a problem. And by the way, this is all depends on the scenario and the data set. But if you choose really like high value k, right, the problem is you end up with too many clusters. In worst case, in extreme case, as many clusters as there are cases and the observations, right? So this is like extreme case. Then basically you missed out a point of clustering. So why you are doing there's no point of doing a clustering, right? So that's why you need to really find the good in the k values. So if the k value is too high, you have a problem, right? Because our goal is reducing the complexity by identifying a much smaller set of coherent cases, right? So our goal of reducing complexity would remain unfulfilled, right? It's not going to be really satisfactory, okay? So the best way to find a good k value is, to plot this total reading SS, right, for each value of k, something like this. And then you typically choose the k value in this area, okay, in this area, okay? If it's too high, you miss out the goal, right? But if it's too low, then you also have a problem, right? So, depends, okay? By the way, that this data is really nice, unrealistically, good, but in reality, it's not going to be this nice. Okay, so in this case, we can really clearly find the elbow area, right? Okay, but anyway, I just want you to, it's good enough to just know the concept, right? So this is how you can typically choose the k value, okay? And now let's just move to the next topic. So there are a couple of more variables that I want you to know when you run this k-means algorithm, right? For example, let's see. So when you run k-means, let's say in this case, the clustering is a 2. I choose k value to be 2, okay? So when you run this, and then when you look at this result, and by the way, just don't worry about the actual implementation, right? Don't worry about the code. Don't even look at the code. So let's say I have a 2, I just did the k-means analysis using 2 clusters, right? And let's just take a look at the result, okay? So I want you to know this couple of variables. I want you to read the results. So that's analysis is very important, right? So now let's take a look at this analysis. So this is my data, age and height, right? And then we saw that in previous lecture, we saw that we have 2 clusters, right? You know what? Let's just maybe, yeah. So let's just plot, just to run this, and then yeah. So okay, now let's just take a look at this. Okay, so we have let's say we have in a cluster, we have 2 clusters, right? And then you know that this is age and height, right? So I want you to look at the result, okay? This, I know that its analysis result could be a little bit different, right? Depending on the programming language, okay? But pretty much the concept is the same. So now when you look at this, there are cluster 1, right? This is the average within the cluster 1, this is average 0.882. Okay, by the way, this is after the Z transformations. Maybe this is not the right graph. I want you to look at the plot. Okay, so now let's look at the Z trans. So after the okay, good. So this is after the Z transformations. Okay, so you know that now this is Z value height. z value, and this is age z value. And if you look at the first cluster, right, the average, average age is minus 0.88. By the way, this is a z value. And then height is, this is like average height. And then this is for the first cluster, and this is for the second cluster. And then finally there's a cluster vector, which is 1, 1, 1, 1. That means this is all what? Belongs to cluster 1. So basically 1, 2, 3, 4, 5, 6. The first 6 data is the cluster 1, right? It belongs to the first cluster, cluster 1. And the remaining 6 data set is belong to what? Cluster 2. So this is cluster 2, right? Remaining 6 is cluster 2. The second cluster. Okay, now the next one is kind of important. Within the cluster sum of square by cluster, and you see that between SS divided by the total SS is 90.7%, which is pretty good. I mean, if this is close, so our ideal goal is like close to 100%. However, if this value is like 60 some percent or like 70 some percent, then usually the that's really considered as a good value. So anything above, let's say 70% or maybe 65 or 70, 80%, right? It's really good. I mean, this is 90%, so this is like superb. Okay, so this is analysis. This is a ratio, right? So let me just first explain about this ratio. Okay, so let's just go back to the slide. Okay, so now before I talk about this ratio, right? Let me first introduce what the total SS really means, right? The total SS, right? And then I'll talk about what the between SS really means. Then I'm going to explain about the ratio. Okay, so first, the total SS. Okay, by the way, let's just start with the within SS. I know that we already covered this, but okay, so you know that this within SS is a degree of incoherence within each group. So important thing here is within, right? Within each cluster. So let's just highlight this. Okay, so within, right? So the high similarity, right? So if there's the high similarity or the high coherence, then within SS value gets smaller, right? And the total SS is the sum of the square distance of each observation. So basically sum of the square distance of all the observation to the overall sample average. Okay, so namely all the variance in the data. So this total SSS is just the fixed value, okay? Regardless of the K, right? Regardless of how many clusters you have, it does not matter. The total SS is just a fixed value because just simply sum of the square distance of all the observation, right? To the overall sample average. So this value is fixed. There's nothing you can do. But between SS, this value changes depends on the K value, right? So how many clusters you have. And just between SS's, I'll just use an example. Let's assume that, oops, I think there's some typo. So let's assume that, we have 3 clusters, okay? 3 of them. So basically then, the sum of the squared distance of this average to the overall average, right? So that's the definition of the between SSS. So basically, the idea is this. The idea is, let me just use the pen. Okay, let's see. Okay, so let's say we have a 3 group. I mean, let's just use the 2 groups just for the simplicity. Maybe it's 3 groups. So the within SS is just within this group, right? Incoherence. The level of incoherence within this group, right? So you have a within SSS, within SS, right? And the between SS, it's, basically the concept-wise, distance between these 2. I mean, this, right? This is like a concept. So this is the, so this is what? Between the clusters, okay? So this is like a, so this is within, right? The total SSS, and this between SS is as the name indicates, is between the clusters, right? So if this value, so if this value, ideally, right? Ideally, when you have a ratio, right, the between SS divided by total SS, the desired ratio is 1, meaning that it's 100%. So basically, if you choose the number of clusters to be the same as the number of observations, right, then means what? Then your between SS is going to be exactly equal. I mean, this total SS or the between SS exactly is going to be between SS is going to exactly as a total SS, so it will becomes 1. You know, as right. So let's say you have all the observations. Let me just use a red. So let's say this is your observations, right? Right. So you have some observation, right? You know what? Let me just. Okay. So let's say you have some observations. So this is the right. So let's say you have some observations, and then each observation becomes a cluster, right? Let's just assume that each of them, you know, becomes a cluster. So we have a lot of clusters, right? So, you know, our number of clusters is the same as the number of observations, right? In this case, obviously, this between SS is going to be same as total SS, right? So the ratio is going to 1, right? The ratio is going to be 1, right? Which is 100% in this case, right? Okay, so I mean, it's conceptually, right? If you have a really, you know, let's say, I mean, since I use the 3 clusters, so let's say if I have very 3 distinct clusters, right? So let's say somehow, right? I know that this is ideal case. Let's say all the observations is within this group, right? And then there are 3 very distinct, you know, clusters, right? That means you will have a high value between SS, right? Which is going to be very close to the total SS. Okay, so once again, if our desired ratio is 100%, is 1, right? So now let's look at the previous our example. So what is this ratio? The ratio is 90.7%, right? Which is close to 100%. So this is really, you know, ideal value, right? 90%, right? So anything I said on anything above like 70%, maybe 65%, you know, considered to be a good value. Okay. And now a couple of more. Let's see. Where is the value? Okay, maybe this is still a good one. Okay, so you know, TOT, you know, within SS is 2.38 for this specific case, right? I already explained about this one, right? The TOT within SS, right? It's summation of these 2 values. So 2.0382, right? So that's the value. And then another one is total SS. That's a 22, right? Total SS is that's 22, right? And you see that it's creating 2 clusters, right? It's obviously, it's really, you know, it's improved. It's going to be a huge improvement, right? From 22 to all the way 2.382. So without clusters, the level of what? The level of incoherence is 22, which is very high, right? But once you create the 2 clusters, the level of incoherence is reduced to 2.03, and please note that TOT dot within SS, you know, represent this number, right? And then in the likewise, this TOTSS, right, is the total, right? Is a total within SS without any cluster. So total TOTSS is what? It's the within SS for the complete data set. Okay, so yeah, so those are the ones that I want to you know, I want you to know, right? So let's just summarize. You know, cluster vector is obvious, and the ratio between SS and total SS, the ratio is very important, right? And then I just explained about this TOT within, what the TOT within and the fit, I mean the TOT SS, what they really mean, right? And what they really mean, okay? I think that's it. Okay, so this is the average, the value for each cluster, and this cluster vector ratio, and this value, and this TOT, within an SS. Yes, those are the variables that you should know, right? I mean, you should know the meaning of these variables. Okay, so good. So I'm done with this, the conceptual introduction to k-means clustering. Okay, so thank you.